Okay, now recording. Right, so moving right along to 16.2 today. Maybe some of 16.3, I'm not sure, but at least 16.2, and I'll give you a quiz later also. The quiz will be on transformations, okay? You may assume that it's already a linear transformation, so you don't have to run through the whole rigmarole that I did last time. We basically just transform the points, so that makes it much easier. Okay, so I've already covered everything I need to for chapter 15. Okay, so we're here now. Game plan for today is 16.2, maybe sneak in some of 16.3, not sure, but we'll see how it goes. Okay, and again, I will let you have next Tuesday, second half of class for questions and answers. If you have any questions in preparation for the test, then you can bring it up then. Looks like I'll most likely be up to 16.3 at that stage of the game. Okay, so question and answer session for chapter 15, Tuesday the 20th, second half of class. So Thursday the 22nd, you have the entire class period for the exam, just like the last test, just like exam 5, and just like the final exam. Okay, so no question and answers. I'll give you the whole time. So we know some of those problems can get long, so I take that into account. So you have the entire class period for the test. Okay. All right, so any general questions before I start doing actual math? Anybody, please? Uh, 15.9 homework. Yeah, I kind of messed up on that one, actually. And well, truth be told, question about 15.9, number 15. Okay, I would just go ahead. I'm not going to give you that entire problem anyway. It's too long. Okay, so I may just have you do a part of it, but thanks for bringing that up. So you can't find the error because the error wasn't with you. The error was with me, most likely. But I figured it's probably not worth it to go down that rabbit hole. Okay, so I don't want to say don't do it at all. Okay, I mean, the setup was good. And I think I just messed up in a certain part of the integration, but the transformation part was especially a good part of that. Okay. All right, so I think we'll just go ahead and get started. All right, so 16.2, again, 16.2 will not be on next Thursday's test. We're doing line integrals, which is really a misnomer. It probably should be thought of as curve integrals. Okay, so we're integrating along a curve. You can think of it as a line because, again, if you chop this up into a whole bunch of pieces, chop, 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 okay, each little piece looks like a quote unquote straight line segment. Okay, so for instance, if I just look at the region from here to here, say, okay, it's almost straight. If I chop it even finer, it's even closer, right? So line integrals really should be thought of as curve integrals. Now, for some of our integrals, we're going to have number 3 in 2 dimensions, f of x, y, ds. ds is a tiny change in arc length. Okay, so we have dx, change in the x direction, dy, change in the y direction, dz, change in the z direction, but ds, the direction of the curve itself. Okay, so in 2 dimensions, ds is square root of dx dt squared plus dy dt squared dt. And in 3 dimensions, you just add a dz dt squared dt. Okay, so what you need to know on page 1076. Yeah, if you want to put this on your cheat sheet, probably the second one. Yeah, this one here. ds is square root of dx dt squared plus dy dt squared. And you know what? You might as well put the 3-dimensional flavor. So put dz dt squared. If it's 2 dimensions, just drop the dz dt, right? So ds, a tiny change in arc length, is radical dx dt squared plus dy dt squared dt. Okay. One possible significance of line integrals, figure 2 is a good example. Okay, so you know how in Calc 1 you have area under the curve for a line segment. Okay, so I have a line segment going from here to here, and I have area under a curve. Okay, now imagine a curve in the xy plane, okay, like this, and you've got a fence, okay, a curved fence, like so, with varying heights. Okay, and so you're trying to find the area of the fence, which is not just along a line segment from A to B, it may be along a curve, right? And of course, this is very practical when you've got curved objects, right? When you have fencing that's not just straight, rectangular and all that, but maybe there's a fence that looks like this. Okay? And the fence in this case doesn't have the same height necessarily, you got varying heights. So you can talk about area under a curve for stuff that looks like this. Okay? So again, very rich in possibilities, which makes you think back again, Calc 1, you kind of want to say, oh, I'm integrating from A to B. It's like, oh, is that all? Right? We're now integrating along a 2D curve, and you can also integrate over a curve in space, right? A space curve, and we can integrate over something like that. So normally what you do is get it down to a single variable. Okay? So for instance here, integrate along the curve 2 plus x squared y ds, and it says you're integrating the upper half of x squared plus y squared equals 1. Okay, so you're integrating along here. Okay, so ds, you have to figure out radical dx dt squared plus dy dt squared dt. If there's a z component, dz dt squared dt. And they may give you parametric equations, change x to whatever it is, change y to whatever it is, and then integrate from there. Now, sometimes you have to take the region and split it into subparts. Figure 4. Okay. We'll have to do some of this, by the way, also. Well, I showed you one last time, that square region, right? So you had an L1, L2, L3, and L4. So here we're integrating over C1, C2, C3, C4, C5. Okay. So to integrate over all of them, you have to find the integrals of each individual part. Right? The integral of the whole thing would be the integral over C1 plus the integral over C2 plus the integral over C3, C4, and C5. Okay, so that might be possible. Figure 5, here you're integrating along C1 and then C2. I guess C technically isn't a curve, it's a straight line segment, but maybe that's part of y equals x squared, I'm guessing, from 0, 0 to 1, 1. And then you integrate going straight from 1, 1 to 1, 2. Okay. So maybe your fence looks like this, right? It's curved like that. And then you're going straight over here. Okay. And maybe the integral is area of the fence, whatever this thing above it happens to look like. Okay. All right, now we still might integrate with respect to x and y if that's all we care about. So we're going to have some problems where you integrate with respect to x, integrate with respect to y. If all you care about is the rate of change strictly in the x direction, or only in the y direction, 5 and 6, or only in the z direction. Okay, so you have blah, 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 dz also. So we're going to integrate dx, dy, dz, and also ds, s meaning change in arc length. Okay. All right, and we're going to rehash this one. So we're going to resurrect this formula we had from a long time ago, page 1079. You want to put that in your cheat sheet. If you have a line segment going from point A to point B, R0 to R1, then R of t is 1 minus t R0 plus t R1 as t goes from 0 to 1. Okay. Straight line segment, either in 2D or 3D. Let me use a 3D example. Of course, 2D can be thought of as 3D and z is equal to 0. Right? You have 2 points in space. This point, this so x0, y0, z0, and you're going to x1, y1, z1. Okay, give a parametric representation of it. That's what you do. Right? A straight line segment from one point to another. I think we have something like that in homework. Okay, so you can re-put that in your cheat sheet. All right, and then page 1080, line integrals in space, formula 9. And yet this is actually more general. So again, maybe you don't have to put the two-dimensional flavor on your cheat sheet. Number 9 will take care of it, right? And if it, so here's a three-dimensional flavor, and if it turns out to be two-dimensional, then just cover that up, right? There is no z, and there it is, right? So f of x, y, z, ds, and ds is a tiny change in arc length in space. So ds is radical dx dt squared plus dy dt squared plus dz dt squared dt. Okay. It's basically the Pythagorean theorem in 3 dimensions. Okay, so maybe we're integrating over something like that in space, figure 9, okay, page 1081. Okay. Figure 10, you're integrating along C1 and C2. So it looks like in space, you're going from 2, 0, 0 in a straight line segment to 3, 4, 5. Then after that, you're going from 3, 4, 5, I guess it's straight down to 3, 4, 0. Again, look at all the different possibilities you have for so-called line integrals or curve integrals. Okay, so again, in Calc 1 and Calc 2, all we have is integral from A to B on basically the x-axis. And now we're pretty much saying, is that all you're doing, right? We got integrals along curves in 2D and even 3D. Right? Now, something, you want this one, 1083. Let F be a continuous vector field defined on a smooth curve C given by a vector function. The line integral of F along C, integral of F dot dr. It looks like a dot product along a curve. Okay, I say you probably don't need this one, even though it's true. But in computation, you're going here. So F of R of T dot R prime of T. It can be thought of as a dot product. Okay. Capital F for a function, quite often it's thought of as a force function along a tiny change in arc length, F dot dr. Okay. So if you're integrating over this space curve, for instance, right? The concept is, chop, 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 and you compute F dot dr for this one, F dot dr for this one. Okay, the function along a little change in arc length, and then here and here, and add them all up, and then chop it into finer and finer pieces, take the limit as n approaches infinity, and so on. Okay, so we'll see this a little bit more later on, but integral of F dot dr. Okay, so some function, it can be thought of as force. It's a good reason to have capital F, but it's a vector function. Okay. And by the way, dr is basically the vector dx, dy, dz. Okay, so I'm going to put that over here. dr is dx, dy, dz. Okay, so we might have to do that from time to time. Right? Okay, so here we go. Get started. Now, most of these problems, you don't have to graph it. You just have to visualize it. Now, if it's 2-dimensional, you can probably graph it. 3-dimensional is a little bit tougher, right? So 16.2, what are we supposed to do? 1 to 21 odd. Okay, so on page 1084, for the benefit of those of you that don't have the book. Getting it. Okay. (17, 19, and 21. Evaluate F dot dr. Okay. And by the way, for 19 and 21, remember R is the position vector that emanates from the origin. Okay. All right, so put the book down most of the time because it's too heavy. Okay, number one, integral along the curve C. We'll use C in general for a curve that includes straight lines. Okay, so that might be part of it. Integral of y ds, and here's the curve defined parametrically: x equals t squared, y equals 2t. Okay, t goes from 0 to 3. Okay, so this parametrically defines a curve, right? If you plug in 0, you're at 0, 0. If you plug in 3, you're at what? 9, 6. If you plug in 1, you're at 1, 2. If you plug in 2, you're at 4, 4, and so on. So it defines a curve. So you're integrating along some curve. Okay, let's pretend it looks like this. Okay. So it's different than in Calc 1 and Calc 2. When you're integrating from A to B, it was just along a straight line segment. Okay, but now we could integrate around a curve in 2D. And of course, I can't draw it, but you could be integrating along a space curve also. All right, so by formula, ds, I need dx dt and dy dt, no big deal. Dx dt, 2t, dy dt, 2. So I do this single variable integral, t goes from 0 to 3, of y, change y to 2t. And then by formula, square root of dx dt squared plus dy dt squared dt. If there was a z component, then there'd be a dz dt squared also, right? So I'm essentially just doing, again, I think it's easy if you just look at the 3-dimensional version, number 9 here. Okay, and if it turns out to be 2D, just drop off the dz dt, right? Page 1080. Well, I'm sorry, I forgot one other thing. You might want this on page 1084. Okay. Another way to indicate integral of f dot dr. F dot dr. F can be thought of as the vector PQR. And dr is dx, dy, dz. So it's integral of p dx plus q dy plus r dz. Okay, so f is PQR. Maybe I'll just write this. F is PQR. dr is dx, dy, dz. So if I take their dot product, I have p dx, there it is, plus q dy, there it is, plus r dz. Okay. All right, so anyway, where are we now? So that's dx dt squared plus dy dt squared, that's 4t squared plus 4, which is 4 times t squared plus 1. Okay, that square root of 4 will come outside as a 2. I'll leave this as radical t squared plus 1. I'm not going to take out that 2 because that's perfect for the substitution, the u substitution, right? If u equals t squared plus 1, du is 2t dt. So I'm integrating radical u. So it's just going to be t squared plus 1 to the 3/2 divided by 3/2 times 2/3. Okay, so that's 4/3. Plug in 3, I have 10 to the 3/3. Plug in 0, I get 1. So 10 to the 3/2 minus 1. And yeah, I got too lazy, but I'll go ahead and write it now. 10 to the 3/2, 10 radical 10, right? Right, that's our standard way of writing something to the 3/2 powers. 10 to the 1, 10 to the half. Okay. Number 3, integral of x, y to the 4th ds. C is the right half of the circle, x squared plus y squared equals 16. X squared plus y squared equals 16. I'm integrating over this part. So imagine walking along the curve, and everywhere on the curve, there are different heights. In fact, here are the heights. What is the integral, right? So again, much more rich in variety than just integrating from A to B, right? All right, if I want the right half, that's x equals radical 16 minus y squared. All right, so if I want to write it parametrically, I can just let x equals radical 16 minus t squared, let y equal t. And t goes from -4 to +4. Okay, if I'm going to write it parametrically, x equals radical 16 minus y squared, just let t equal y, then x equals radical 16 minus y squared, or radical 16 minus t squared. Okay. All right, so dy dt is easy, 1. Dx dt, 1/2, 16 minus t squared to the -1/2, times the derivative of 16 minus t squared, which is -2t. The -2 cancels to 2, so best form is -t over radical 16 minus t squared. All right, so by formula, I need dx dt squared plus dy dt squared. So dx dt squared is very nice. First, you lose the negative, right? And this comes out to be dropping the square root. So I have t squared over 16 minus t squared plus 1, the common denominator, right? So if I add these together, I just have 16 over 16 minus t squared. All right, so I'm ready to integrate. X, y to the 4th. X is this thing. There's x. Y to the 4th is t to the 4th. And then ds is radical 16 over 16 minus t squared dt. And very, very conveniently, this thing cancels this thing. I just have a polynomial, t to the 4th. Okay, so radical 16 is 4. So 4 comes outside, that cancels. So 4 t to the 5th over 5. Okay, which is 4/5. Okay, 4 to the 5th is 1024 minus -4 to the 5th is -1024. So grind this all out. 8192 over 5, or 1638.4. And that's my final answer. All right, so hopefully that wasn't too bad. Now for a much worse problem, 7. Integral along C of x plus ty dx plus x squared dy. By the way, that looks like p dx plus q dy, or f dot dr in 2 dimensions. Okay. C consists of line segments from 0, 0 to 2, 1, and from 2, 1 to 3, 0. Okay. This is like your P. This is like your Q. So this is what they say is f dot dr. In 2 dimensions, dr is dx dy, and the f they give us is x plus 2y comma x squared, so to speak. And here's what we're integrating over. Okay, so you're going from 0, 0 to 2, 1. I'll call that C1. And then from 2, 1 to 3, 0, I'll call that C2. All right, so let's write what these things are. Okay, so C1, that's y equals a half x. I'm going from 0, 0 to 2, 1. You could do that game of, the parametric equations going from one point to another point, but these are easy enough. You know that from algebra 1, right? So y equals mx plus b, slope is 1/2. So c is 1/2 x, x goes from 0 to 2. This one has a slope of -1. If I were to extend it, the y-intercept would be 3. Y equals -x plus 3, x goes from 2 to 3. Okay, and let's see, right here, dy is equal to half dx. C2 dy is -dx. Right, so I basically just plug everything in. So integral along C is integral along C1 plus integral along C2. So I figure this integral out and this integral out. Okay, so C1, x is going from 0 to 2. Stuff that I need is y and x going from 0 to 2, dy and dx. Okay, so I'm basically plugging this in. Okay, x plus 2y, x plus 2y, y is a half x, right? Dx plus x squared dy. Dy is 1/2 dx. Okay, C2, again, we said y equals negative x plus 3. X goes from 2 to 3. Okay. Just find the slope and do the point slope form. And by the way, if you're not convinced, you can plug in the 2 points. Plug in 2, you should get 1. Plug in 2, yes, you get 1. Plug in 3, you get 0, yes. Okay, so let's clean this up. So that comes out to be x plus 1/2 x squared dx, right? There's x plus another x plus 1/2 x squared dx, or 2x plus 1/2 x squared dx. Integrating as x goes from 0 to 2. I could integrate with respect to y, but we're more comfortable integrating with respect to x. So that comes out to be x squared plus 1/2 x cubed over 3 from 0 to 2. Plug in 0, you get 0. Plug in 2, 4 plus 8 over 6, which is 5 1/3, 16 over 3. All right, then along C2, x is going from 2 to 3. So x plus 2y dx. X plus 2y, here's y for the second graph. You can see these problems can get really long and really intense. There's x plus 2y. For the second graph, that's y dx, plus x squared, where'd it go? X squared dy. Dy is negative dx for the second curve. So x squared negative dx. All right, so that's negative x squared. X minus 2x is a negative x, and then plus 6 dx. So that's my integral. Okay, so negative x cubed over 3 minus x squared over 2 plus 6x from 2 to 3. Unfortunately, this time I don't have a 0 that I can plug in. Plug in 3, negative 27 over 3, which is negative 9, minus 9 over 2, plus 6 times 3 is 18, minus, plug in 2, negative 8/3, minus 4 over 2 is 2, plus 12. Okay. So I worked it all out. It comes out to be negative 17 over 6. Okay, you can check over all my arithmetic over here. Theoretically, it should work out. Okay, negative 17 over 6. All right, so finally, the integral along C is the integral along C1 plus C2. So integral along C1 was 16 over 3. Along C2 was a negative 17 over 6. So I just combine them. Final answer is 5/2. Okay, so the whole idea was to get it down to a single variable. I got everything down to just x. So I needed to change y over, and I needed to change dy over. And I had to do it twice because I had C1 and a C2 involved here. Okay. All right, that's the end of that side. So let me do my focus thing again. Okay. Okay, let me try 11. So that one, you're going from one point to another, so you can see how that works. So this is in space now, 3D. 11, integral of x e to the y z ds. C is a line segment from 0, 0, 0 to 1, 2, 3. Okay, this should be pretty easy. If you're going straight from here to here, x is t, y is 2t, z is 3t, t goes from 0 to 1. That pretty much does it. Yes, you could use that other formula. It works. But for this formula here, R0 is the 0 vector. You're starting at the origin. So it's just t times R1, 1, 2, 3. So it's 1, 2, 3 times t. So here are parametric equations for that line segment. Okay, so ds is the square root of dx dt squared, 1 squared, plus dy dt squared, 2 squared, plus dz dt squared, 3 squared, radical 14. Okay, so I just plug everything in. X e to the yz. X was t, e to the y is 2t, z is 3t. Take out the radical 14 as a constant. So I have t e to the 6t squared dt. Okay, then by u substitution, if u is 6t squared, the derivative is 12t. So I need a 12 inside and a 1/12 outside. So you'd be integrating e to the u. What's e to the u? E to the 6t squared. So I have radical 14 over 12, e to the 6t squared from 0 to 1. Plug in 1, you have e to the 6. Caution, when you plug in 0, you do not get 0, right? E to the 0 is not 0, e to the 0 is 1. So final answer, radical 14 over 12, e to the 6th minus 1 this time. Okay. All right, then 15. C is the line segment from 1, 0, 0 to 4, 1, 2. Okay, so we can use that formula I showed you. And that's like the f dot dr, where f is z squared, comma, x squared, comma, y squared. Dr is dx, dy, dz. All right, to show you a little bit more, the book calls this P, Q, and R. F dot dr. I'm trying to show you here. Integrating f dot dr. So f is the vector pqr, dr is the vector dx, dy, dz, and the dot product is p dx plus q dy plus r dz. So f has components p, q, and r, as you can see there. Okay. Okay, so if I go from 1, 0, 0 to 4, 1, 2, I'll use that formula this time that we showed you just a moment ago. And remember, that only works if it's a straight line segment. If you don't have a straight line segment, can't do it. So R of t by formula is 1 minus t R0 plus t R1. T goes from 0 to 1. It's very nice because you can't get any better than integrating from 0 to 1. R0 is 1, 0, 0 written as a vector. It's a position vector. R1 is 4, 1, 2 written as a vector. So instead of parentheses 1, 0, 0, write it as vector 1, 0, 0. So 1 minus t times that plus t times 4, 1, 2. Okay, let's multiply it out. 1 minus t times 1 is 1 minus t plus 4t. And then 1 minus t times each of these is 0, right? So ignore it. So I have 1t for the middle one, and the last one is 2t. So it comes out to be 3t plus 1, combined to 3t plus 1, t, and 2t. So here's what I have. And very easy way to double check it. You're going from 0 to 1. Plug in 0, you have 1, 0, 0, correct? Plug in 1, you have 4, 1, 2, correct? 4, 1, 2. So you know you did it right. which basically means x equals 3t plus 1, y equals t, z equals 2t. Okay, so the next job is to write everything in terms of t. Okay, dx is 3 dt, right? dy equals dt, dz equals 2 dt. Okay. Technically, you could say this was differentials in Calc 1, right? The Leibniz notation in Calc 1, you would say dx dt is 3, just multiply both sides by dt, and it looks like this, right? Dx is 3 dt, dy is dt, dz is 2 dt. Okay, so now getting back to this equation, this integral, t is going from 0 to 1. I have x, y, z, dx, dy, dz. Every time I see x, I write that. Every time I see y, I write that. Every time I see z, I write that. Dx, I'm going to write that. Dy, I'm going to write that. Dz, I'm going to write that. So I'm only going to have t now. That's the key thing. Get it all down to a single variable. Okay, and just to make it easier for myself for reference, z squared dx, I wrote it here. X squared dy, I wrote it here. And y squared dz. So now I'll just pick up the parts that I need. So z squared, right? That's 2t quantity squared. And then dx is 3 dt. Plus x squared, 3t plus 1 squared. dy is the same as dt. And then y squared is t squared. And dz is 2 dt. As you can see, there's a lot of stuff here, and it can get really long. Okay, but now I just have a bunch of dt's. So I just take the dt out and simplify all of this. So that's going to be what? 4t squared times 3 is 12t squared. And that's going to be 9t squared plus 6t plus 1. And that's 2t squared, right? Okay, so combine like terms. 12 plus 9 plus 2 is 23t squared plus 6t plus 1. And now that's a fairly easy integral. Okay, so 23t cubed over 3 plus 3t squared plus t. From 0 to 1, plug in 0, you get 0. Plug in 1, 23 plus 3 plus 1. 3 plus 1 is 4. 4 is 12 over 3. Final answer, 35 over 3. Okay. All right, 17, just ask you to look at the picture. Let F be the vector field shown in the figure. So here's a vector field, like in section 1, right? So it's spinning around a circle. That would be a clockwise direction, I guess. So each of these can be thought of as a little dr or ds. As a vector, it's dr. Okay. As a line segment, it's ds. So what's the difference between dr and ds? Dr is a tiny change in the vector. ds is not a vector, but it's still, in space, it's going from here to here. But if you change it to a vector, it's a dr. So here's all the drs. So they're saying, just give the correct sign, sign. Hey, if C1 is the vertical line segment from -3 to -3, 3, determine whether the integral of f dot dr is positive, negative, or 0. Okay, so if we go in a straight line from -3, 3 to -3, 3, so you're going from here to here. Okay, so you're going with the flow, so to speak. You're going in the same direction as flow, so that's going to be positive. You basically just look at the arrows. So 17a is positive. Okay, if you chop this up in a whole bunch of pieces, f dot dr, okay, you're going in that direction, so that'll be positive. Okay, part B comes out to be negative. Let's see how come. C2 is a counterclockwise oriented circle with radius 3 and center at the origin, determine whether the integral of f dot dr is positive, negative, or 0. So radius of 3 counterclockwise. So you're going this way. Okay. If I'm going that way, but all the lines are aiming the other way, counterclockwise. So that's why this one comes out to be negative. Okay. All right, here we go. Okay, we only have a couple of problems left. 19 and 21. Evaluate f dot dr. Okay. We'll see that f dot dr quite a bit more later on, but that's where I use this thing. Line integral of f along c. So f dot dr. So see that f of r of t? You basically just plug in, and then you need r prime. Then you take the dot product, and hopefully you're down to a single variable dt. That last one, f dot t ds, you're normally not going to do that. So even though it's true, I would say don't bother putting that in your cheat sheet. You're not going to have any homework problems involving that. Okay, so 19, two-dimensional. F of xy is xy squared I minus x squared j. And r, remember r is a position vector. T cubed I plus t squared j, t going from 0 to 1. Okay. Okay, so f, as you know, I prefer the angle braces, so I don't have to write I and j that much. I just write it, quote unquote, occasionally. So I write f as xy squared negative x squared. It's the same as I and j. And r is t cubed t squared. All right, I plug in. So everywhere I see f, everywhere I see x, change it to t cubed. Everywhere I see y, change it to t squared. That's essentially what this means. Previous page. See what says f of r of t? Just plug in for r of t, for x and y. So here we go. X, y squared, right? X is t cubed, there's x. Y squared is t squared squared. Okay, that's x, that's y. Maybe I'll emphasize that more by writing it. X, y. Remember, r is always a position vector. So if it's a position vector, the components are automatically x and y and z. That's not necessarily true for f. Well, you can see f, that's not x and that's not y. Okay, it's just any other vector. Okay, so xy squared is t cubed times t squared squared. And then negative x squared is negative t cubed squared. So the new change vector f is t to the 7th, negative t to the 6th. If I change everything to t, correct? Okay, so one more time. T cubed is x. So I put t cubed there and put t cubed there. And y is t squared. So put t squared there. So I have x, y squared is t cubed, t squared squared, negative t cubed squared. So t to the 7th, negative t to the 6th. So that's the new f. And then I need r prime, dr. That's easy. So that's 3t squared, 2t. You can think of that as dx and dy. So 3t squared, negative 2t. Take their dot product. That times that is 3t to the 9th. That times that is negative 2t to the 7th. So the integral of f dot dr is I'm integrating 3t to the 9th minus 2t to the 7th from 0 to 1. Okay, so that should be pretty straightforward. Okay, so 3t to the 10th over 10 minus 2t to the 8th over 8 from 0 to 1. Plug in 0, you get 0. Plug in 1, you have 3/10 minus 1/4. Common denominator is 20. So 6 over 20 minus 5 over 20. Final answer is 1/20. Okay, folks, so it's our usual time to break. I'm almost done. I was going to show you 21. So maybe after the break, I'll do that one problem. I'll sneak in, quote unquote, a little of 16.3, which will make it easier for me next time. And then I'll go ahead and give you the quiz. All right. Okay, so we'll break until 7:10-ish as usual. Okay, folks, it's 10 after. We'll go ahead and start and finish up pretty quickly. Won't go that much longer, then give you the quiz and call it a day. So all I had left to show you was 21. And then I'll sneak in some of 16.3. Okay, I may not do any problems. It'll take a while to develop some of the ideas in 16.3. Okay. A lot of physics applications. Actually, this entire chapter is a lot of physics applications for you physics people out there. All right, so 21 is a three-dimensional flavor of problem 19. Evaluate integral along C of f dot dr. So f of x, y, z is sine xi plus cosine yj plus xzk. And the position vector r is t cubed I minus t squared j plus tk. T goes from 0 to 1. So here's f of x is given to be this. And they said I, j, and k. I'm too lazy to write the I, j, and k. I just put this. And there was r. And again, they gave me I, j, and k. I'm just going to write it like that. Okay, keep in mind for r, this is x, y, and z. This is a position vector. Okay. F is not a position vector. You can tell it's not x, y, and z. It's sine x, cosine y, and xz. Okay, so if you want to get the notation straight on what's happening, this is what the text calls P, Q, and R. But for position vector R of t, this is indeed x, y, and z. So x, y, z. All right, so the first thing I do is change x, y, and z into t cubed, negative t squared, and t. Remember, this is a position vector. So that's going to be sine of x is sine of t cubed, right? Cosine of y, that's cosine of negative t squared. And then x times z, x, z is t cubed times t, or t to the fourth. And then r prime, or dr, that's easy. So derivative is 3t squared, comma, negative 2t, comma, 1. So I take the dot product, f dot dr. Dr can be thought of as r prime also. So that times that, 3t squared sine of t cubed. That's perfect for u substitution, right? The derivative of t cubed is 3t squared. And then negative 2t cosine of negative t squared. That's also perfect for u substitution. The derivative of negative t squared is negative 2t. And then t to the fourth times 1 is t to the fourth. Well, that's already easy to integrate. You don't have to worry about that. All right, so I just integrate from 0 to 1. So the integral along the curve C of f dot dr, and this is a curve in space defined this way, right? Integral of 3t squared sine t cubed minus 2t cosine of negative t squared plus t to the fourth dt. Okay, if I were to do a u substitution, u equals t cubed, du is 3t squared, right? So I'm integrating sine u, negative cosine u, negative cosine t cubed. Likewise here, if I did a u substitution, u is negative t squared, du is negative 2t dt, it's perfect. So I'm integrating let's see. Let's see. Not sure about something. I got plus sine of negative t squared. To think about that. I know I got the correct answer, but something bothers me about that. Anyway, let me finish this. T to the fifth over 5. Okay, I think I know what's happening here. Or maybe I don't. Oh yeah, after I substitute, it'll be a positive. That's right. But then it's positive, negative 2t cosine negative t squared. Okay, I think we're good. Okay, plug in 1, negative cosine 1 minus sine of 1. This is 1 radian. We don't know what that is. Plus 1/5. Plug in 0, negative cosine of 0, which is 1, plus 0, sine of 0 is 0, that's 0. So this is negative negative 1. 1 plus 1/5 is 6/5. So final answer is 6/5 minus cosine of 1 radian minus the sine of 1 radian. And that's as good as it gets. You just have to leave the answer like that. And we're finished. Okay, so I'm done with the section. And I'm not sure if I remember doing my focus thing, so I'll do that rapidly again. So here's all of 16.2. I'll sneak in some of 16.3 since we have time. And then I'll give you the quiz. Try to give you most of the theory at least. That. And all that. And while I'm showing you this, so yeah, for sure, that 70% homework rule for tests, that's, you know, I end up doing sometimes 70% or even more anyway. Oh, you don't want to see that because I messed up. Right. Okay, so I'll mark that down. I'll introduce 16.3. Put that on my calendar now. So I'll definitely do 16.3 next time. Not sure about 16.4. Again, I'm going to leave question and answer session for Tuesday in preparation for the test on Thursday, okay? So 16.3, mostly introduction. Page 1087. Fundamental theorem of calculus for line integrals. Which to me doesn't really explain everything that's going on here. To me, the main topic is conservative vector fields. And this is where we get our conservation laws in physics, especially. Very useful. All right, so theorem 2, you want it on page 1087. Put this on your cheat sheet, even though you may not know what it means now. Let C be a smooth curve given by the vector function r of t. T goes from A to B. F is differentiable function of 2 or 3 variables. It actually could be more, 4 variables, but we hardly do those. Whose gradient vector del F is continuous on C. Okay, the integral along C of del F, gradient of F dot dr, is F of R of B minus F of R of A. That kind of looks like the fundamental theorem of calculus from Calc 1. You basically plug in the end point, plug in the beginning point, and subtract. Okay, in Calc 1, that's like integral from A to B, capital F of B minus capital F of A. This is similar. You just plug in the ending point, the beginning point, and subtract. Okay. Little f is a 2 or 3 variable function. Del F is its gradient. Okay. So if this is mysterious right now, it probably should be. Just put it down, but you're going to be using that. But that saves a lot of work. It says in certain circumstances, rather than integrating along the curve, just plug in the ending point, plug in the beginning point, subtract, and you're done. Okay, so certain things have to hold in order for that to be true. Okay, first thing, we have something called independence of path on page 1088. Independence of path, or sometimes path independence. Okay, suppose you're given 2 curves, they call it C1 and C2, of del F dot dr. Okay, that's the same del F dot dr as here. Now it's not just F dot dr, it's del F, which means the result of a gradient. Okay, it's the gradient of something. That's a little bit different than this F dot dr. That capital F there doesn't have to be the result of the gradient of some little f. This one does. Okay, so del F, it's a vector. It's the gradient of some other little f. Okay, we have something called path independence. If you get the same answer along any two curves, as long as the beginning and ending point are the same. That's what they're saying there. So integral along curve 1 of del f dot dr is equal to the integral along C2 of del f dr. That's called independence of path or path independence. Okay. That's going to lead to something called a conservative vector field. Okay. So if you have that property, it's a conservative vector field. And the laws of conservation from physics, I'm guessing, I'm going to speculate all of you have had some physics, whether in high school or now in college. And that gives you the conservation laws. Okay, so concept, I suppose, say conservation of energy. You have point A and point B in space. Okay, let's say some kind of energy, maybe potential energy. Okay, if I go from here to here in any path, okay, I'll have the same answer. So if I go straight there, if I swing around all over and then end up here, or go wiggle around like that and end up here, okay, path independence means it doesn't matter how you get there, as long as you're going from point A to point B, if you always get the same answer, that's what we call path independence. Okay. And that's what's called a conservative vector field. Okay, so that leads to the conservation laws, like conservation of energy. So if I have a potential energy, let's say from here to here, it doesn't matter how I go from here to here. If I go in a straight line or do all kinds of wiggly stuff and end up here, you'll end up with the same difference in potential energy, let's say. Okay. That's something called path independence. Okay. And that leads to a conservative vector field. So they're one and the same. If you have a conservative vector field, you have path independence. Okay. And that leads also to this. On 1089, if you go along a closed curve, okay, starting at any point are the same. So integral of f dot dr is independent of path if and only if the integral of f dot dr is 0 for every closed path C in D. And that makes sense too. See? So if I start here, I go whatever, I end up in the same place, then I could have the same potential energy. Okay, and this could be other types of energy, you know, energy of, you know, electromagnetic energy, right? So again, all the other conservation rules that are in physics. Okay, because if I were to do this integral, okay, f of r of b minus f of r of a, starting point at any point. Well, the starting point and the ending point are the same. So when you subtract, you're going to get 0. And if that happens all the time, okay, then you have a conservative vector field. Okay, so one theorem is that if along any closed curve, you always get 0, then you have path independence also. So a certain amount of potential energy. If you're here, you have a certain amount of potential energy. Now you can go down and squiggle or whatever. You end up in the same spot. You have the exact same potential energy as before. Okay. And again, this leads to all the conservation laws in physics, of which there's a whole bunch, right? Conservation of energy, conservation of momentum, conservation of angular momentum, conservation of charge, perhaps, electric charge. What else is there? Yeah, conservation of energy, conservation of mass, perhaps. Right? So all of those things are there. Okay. Next theorem. Suppose F is a vector field that is continuous on an open connected region. If the integral of f dot dr is path independent path, then F is a conservative vector field. That is, there exists a function little f such that the gradient of little f is capital F. Okay, I write that as an anti-gradient, kind of like anti-derivative. Okay, if you say, what is this little f and capital F? Okay, what's the difference between little f and capital F? Little f is not a vector, it's a scalar function. Let's pretend it's three-dimensional. So little f of x, y, z. Okay, capital F of x, y, z is a vector. Okay. Now you might recall you can take the gradient of little f. How do you do it? It's fx, fy, fz, and you come back with a function. Okay, that's a vector. Okay, so if I take the gradient of little f, a scalar, you come back with a vector function. Okay, and we'll be computing that anti-gradient. So when I go from little f to capital F, I'm doing the gradient. We're going to be going backwards from capital F to little f. Okay, I coined the term anti-gradient. It's not standard. I don't think the book uses that anywhere, but I think you get the idea. I don't know if you feel like you can try to look it up on the internet if there is such a thing as anti-gradient, but if not, you know what I mean. Okay, to go from little f to capital F is gradient. So to go the other way, anti-gradient, just like derivative and anti-derivative. Right? In fact, you are doing anti-derivatives when you find this anti-gradient. How can we tell if we have a conservative vector field? Okay, so let me just go back and say all of these things are equivalent. Okay, the fundamental theorem of calculus holds. Del f gradient of little f dot dr, f of r of b minus f of r of a. Just plug in the ending point and the beginning point. That's only if you have a conservative vector field. If you have a conservative vector field, you have path independence. Doesn't matter which path you pick. If you have a vector field F, you can find an anti-gradient. You're not always going to be able to find this anti-gradient, by the way. All right, so now how can you tell if we're given one of these things, if we have path independence? Okay, so we know f dot dr in 2 dimensions, p dx plus q dy. In 3 dimensions, just add r dz. So how do you know if you have path independence? Okay, so for 2-dimensional, the 2-dimensional flavor is much easier than the 3-dimensional one. Page 1090. Put this on your next cheat sheet. Okay, so this is 2-dimensional. Maybe I'll put down 2D here for emphasis. Okay, F is PQ, P of XY, Q of XY. If you have a conservative vector field, then this is true. The partial of P with respect to Y is equal to partial of Q with respect to X. So if this is true, you have a conservative vector field. If it's not true, you do not have a conservative vector field. Okay, the explanation is actually quite easy based on Claro's theorem. Okay. P, if you can find this anti-gradient, little f, then P would be partial of f with respect to x, and Q is the partial of f with respect to y. Which means if I now take the partial of P with respect to y, I'm taking the second partial with respect to x and then with respect to y. If I take the partial of Q with respect to x, I'm taking the derivative of this with respect to x, partial with respect to y, and then the partial with respect to x. But we know from Claro's theorem, these are equal. Okay. We're actually starting at level 1 of the elevator, as it were. If this level is the original function, little f, then here's the first derivative level, the first partials, and the second level down is the second partials. Okay. We're going to be starting at the first level down. We're already at the first derivative. Okay, so if there is an anti-gradient, meaning if I take the derivative with respect to x, I get p. If I take the derivative with respect to y, I get q. Then if I take this derivative with respect to y, I got that. If I take this derivative with respect to x, I get this, and we know that these are equal by Claro's theorem. Okay, so if I get these not being equal, then we know there is no such function. There is no function little f that has this property. Okay, so that's the 2-dimensional version. I'll give that to you here. And this is actually the converse, but for the functions that we know of, okay, we'll be given a function in 2D. So how do I know if it's a conservative vector field? take the partial of p with respect to y, partial of q with respect to x. If they're equal, you have a conservative vector field. If they're not equal, you don't have a conservative vector field. That's all there is to it. Okay, example. Look at example 2. Capital F of x, y. Is it conservative or not? Okay, so this is p, this is q. So I take the partial of p with respect to y, -1. Take the partial of q with respect to x, 1. They're not equal. So therefore, capital F is not a conservative vector field. So there is no little f, there's no anti-gradient. You're not going to be able to find it. Okay. On the other hand, example 3, 2-dimensional, capital F of x, y, 3 plus 2xy, that's my p. X squared minus 3y squared, that's my q. Okay, what's the partial of p with respect to y? Derivative with respect to y is 2x. What's the derivative of this with respect to x? It's also 2x. They're equal. Therefore, capital F is a conservative vector field. Okay, so you have to admit that's really not that hard. Okay, now it's a little bit of a work to actually find that anti-gradient, but it's a lot of differentiating, anti-differentiating. You just kind of get the algorithm, then you know what to do. Okay. All right, and they talk a little bit about conservation of energy. So this is useful: conservation of energy, conservation of potential energy, perhaps. Okay, and then the problems start, which I'm not going to do. I'm just about to give you the quiz, unless anybody has a question about something. But let me just show you what the homework involves. I'll do that next time. So 16.3, 3 to 21 odd. All right, so the first problems, determine whether or not you have a conservative vector field. 2-dimensional. So you take the partial of p with respect to y and the partial of q with respect to x to see if they're equal. But if it is conservative, they want you to find little f, the anti-gradient, such that del f is equal to capital F. Now I have to show you how to do that. Okay, so that's how those go. Then 13, 15. Looks like they're asking you to find the anti-gradient. Notice in 15, it's 3-dimensional, but they're telling you already there is an anti-gradient. Okay, we don't have a rule yet to tell us how to do that in 3D, but they're telling you already it is the gradient of some little f. So we'll just go with it. Okay. And same for 17, it's 3-dimensional. So how do you know it's conservative? You don't. They just tell you ahead of time there is going to be a conservative vector. It is a conservative vector field. You can find an anti-gradient. Okay, and then 19. Yeah, you can tell 19, it says C is any path from 1, 0 to 2, 1. So if it's any path, you have to have path independence, right? If you don't have path independence, then it's going to matter if I go like that or whatever, but there must be path independence, in which case I'll be using the fundamental theorem of calculus for line integrals. This thing. All right, so that's my introduction to 16.3. It'll just make it easier for me next time. Okay, so I'm done. Unless anybody has any questions, you can put it in the chat right now or unmute yourself. But next time, 16.3, maybe sneak in some of 16.4. Okay, but again, I'm going to reserve the second hour for questions and answers, and then we'll have all of next Thursday, a week from today, for the exam. Okay. So anybody have any questions? Otherwise, we'll go straight to the quiz. Right. Don't see or hear anything. So here we go. So get your cell phones out, or you're ready to do a screenshot. And I'm going to make it very easy on you by not proving that it's a linear transformation. All right, so given the square region in the XY plane bounded by 0, 1, cross 0, 1, it's a square region, right? So find and graph the transform region in the UV plane under the transformation U equals X plus 2Y, V equals 2X plus Y. It's very, very easy, actually. Okay, just take the 4 corner points, plug them in, and see where the 4 corner points go to. All right, so the 4 corner points are what? 0, 0, 0, 1, 1, 0, and 1, 1. Just plug them in. Graph the new transform region in the UV plane. Okay, you don't have to prove that it's linear, so you just connect them with a straight line segment. Okay, now I went ahead and proved each one was a straight line segment, but you don't have to if you don't want to. Okay, although maybe after the quiz, if you want to practice on your own for that, that's a lot more work, but it can be done. Okay, I'll give you just another 15 seconds or so. It's not that hard a quiz. Okay, you basically just plug in the 4 corner points, see where they transform to, and then go from there. Okay, I will assume that everybody has this now. So I'll make this disappear, set up your groups. I'll stop the share. Recording is now stopped.